I want to give an overview of circular motion and gravitation. The key concepts are, first of all, uniform circular motion, which we've looked at before, and centripetal acceleration. So as you recall, for uniform circular motion, an object is going at a uniform omega angular velocity about a fixed center O at some radius r away from O. And so the key quantities are omega, which is in rads per second, and omega is related to the period t as 2 pi rads over t seconds, t being the time it takes for the object to go around once. The linear velocity is continuously changing direction. In magnitude, it is v equals omega times r. Omega is the radial angular velocity and r is the radius. And then the acceleration is always pointing inward, and so it too is changing direction continuously, and its magnitude is omega squared times r, or alternately v squared over r. Either one of these is okay. Second big idea, and this is a new one, is Newton's law of gravitation. And Newton's law of gravitation says that if we have two masses, m1 and m2, separated a distance r, that they will attract each other. m2 will attract m1, m1 will attract m2, and the magnitude of the force is equal to the product of the masses times a big G, which is a constant, divided by the separation squared. So it's termed an inverse square law. So you note these two vectors are in equal and opposite directions, and therefore Newton's law of gravitation is consistent with Newton number 3, as it must be. Thirdly, concerning the concept of weight, close to a planet, the force of the planet on a mass m is the weight of m. And so if you're on the surface of the planet, the force of the planet on m is just m times g, where g is the g of the planet, 9.8 on the Earth, 10 meters per second if you're using easy numbers. But as you go up off the surface, the weight of m decreases, and it decreases according to this inverse square law. More about that later. Fourthly, it is possible to put satellites in orbit around the Earth, and so here is a picture of a simple such situation where the satellite is executing uniform circular motion. One of many types of motion it can have. We're going to focus on just this simple example. The Earth is at the center, and the satellite is at some radius r with respect to the center of the Earth. And the key thing to note there is that gravity, pointing radially inward, provides the force, a radially inward force required to get the centripetal acceleration that's required for UCM. Lastly, there's a concept of weightlessness, and weightlessness simply means the lack of normal force on a mass m. And we'll see some different examples of this, but one we've already talked about is the example of a falling elevator. So that's inside this magenta balloon up here. If you consider an elevator that's accelerating downwards with a mass m inside of it, if the acceleration with which the elevator is accelerating downwards is less than g, the free body diagram will look something like this. There will be the non-contact force mg pointing down, and then the force of the floor upwards on the mass m, the normal force in other words. And Newton number 2 then says if A is downward like this, that ma is going to be mg minus n. In other words, n is going to be m times g minus a, with a little algebra between these two, which is clearly less than the full weight of the mass m. So you can see as this a gets bigger and approaches g, n will get less, and in fact when a is g, which would correspond to cutting the cable and letting the elevator accelerate down at 10 meters per second, n would be 0. In other words, if you were standing on a scale inside such an elevator with a broken cable and it was accelerating down at 10 meters per second, the scale you were standing on would not register any weight. Why not? Because since there's no normal force of the weight pushing on you by Newton's third law, you can't be pushing on the scale. Ergo, your weight is apparently 0.